Take a look here. You may recall that an angle bisector divides an angle into two congruent angles. It cuts an angle in half. We talked about segment bisectors yesterday, perpendicular bisectors specifically, but we were cutting segments in half at a 90-degree angle. Today, the angles will definitely be a little bit different than 90 because we're going to be cutting angles in half. So maybe some of them are 90, but definitely not all of them. So our first thing that we're going to be learning about today is this theorem here called the angle bisector theorem. So this is going to be a little bit different than the perpendicular bisector stuff we talked about the other day, but it'll still look relatively similar. By the way, today we are going to be over to the side here, if you're wondering what we're going to be learning. We're going to be able to prove theorems and solve problems about angle bisectors. We're also going to prove theorems and apply geometric methods to solve design problems and angle bisectors of triangles, using the angle bisectors of triangles. So, an angle bisector theorem. So this says if a point is on the angle bisector of an angle, for example, F, that point F is on the line that cuts this big angle in half, which means that F is on the angle bisector of angle DBE. So if this point right here is on the angle bisector, then it is equidistant, same distance, from the sides of the angle. So that means that from F to D is the same distance as from F to E. That's what we're saying. So basically, if you split an angle in half, cut it straight through the middle, if you put a point on that line that cuts the angle in half, that point will be the same distance from each side of the angle, which makes sense because if the degrees are the same on each side of that angle, then the distance should be the same from that line to each side of the angle. Now, the word distance, equidistant, the word distance actually does have a little bit of a technical definition to it. Distance from a point to a line. So if we're going from point F over here to this line here through B and D, distance is always perpendicular, always. That's a really important thing to know because if we're talking about like from F to the line, you could be thinking like that, which that is not the distance from F to the line because this line is not perpendicular to that. This line is perpendicular to that. So distance means perpendicular distance. That's a really important thing to know here, even though it wasn't specifically stated. So if we chose another point right here, that point is the same distance from this line to that line, but it needs to be perpendicular. So perpendicular here, perpendicular here. That's the only way we can talk about distance is if a point to a line, the distance must be perpendicular. Because otherwise, like I mentioned, it could be any random distance, like from here to here, which is clearly not the same as from here to here. This one is not the same distance, it's longer. So that's a detail that we need to make sure we're paying attention to. So what the result here says, so if ray BF, so from B through F, if that ray bisects angle DBE, so angle DBE is being cut in half, and you can see that down here that we've got the little congruent markings to show that they're the same. That means that FD is perpendicular, and not means that, and FD is perpendicular to BD, meaning it's the actual distance, and FE is perpendicular to BE, meaning FE is the distance, then DF is the same as FE. So we can put a congruent marking there to say that those two lengths are the same. And then beyond that, we could also say, we have enough information now to say that the triangles that are in here, triangle BFE and triangle BFD are congruent because if you take a look here, we've got this length in the middle. You don't need to write this down, but the distance between B and F is on both triangles, which means it has to be congruent on both triangles. And what types of triangles are these two? They're right triangles, yeah, because there's a right angle there, which means that's a right angle as well. So we've got right angles here and here. So that means that the two triangles are congruent because we have a right triangle with a hypotenuse the same on both and a leg congruent on both. so we can use the HL theorem to prove that those two triangles are congruent. So we can also use, what else could we use? Because that angle is congruent, so we could go with side and side, because if these two angles are congruent, those are both 90, that means those have to be congruent. So you could say side and side as well if you don't do right. But the point is, we actually have two congruent triangles between those two. All right, next, we're going to talk about the converse. Converse just means we're going to flip around the phrasing. So if the segments are the same length, so if the distance between D and F is the same as the distance between F and E, that means that point F is on the angle bisector, which means that BF is the angle bisector of angle DBE. So it says if a point on the interior of an angle, point F, it's inside the angle, is the same distance from both sides of the angle, then it is on the angle bisector, or it's on the bisector of the angle. So that's what we're dealing with here. So in terms of math for us, what that means is, if we take a look at our first example here, it says that RT is the angle bisector of angle QRS. And if RT is the angle bisector of QRS, that means that T is the same distance from Q as it is from S, which means that QT and TS are congruent. So on the left side over here, we're going to fill that in with QT. QT is equal to ST. And then we can substitute in for each of those expressions. What should we write here? What does it tell us that QT is equal to? 4x plus 8. Good. Substitute in for 4x plus 8. And then over here, equal to what? Yeah, 9x minus 7. All right, so to get to -5, it looks to me like they subtracted 9x from both sides to get -5 there, which means we need to subtract 8 from both sides to get what on this side? What's -7 minus 8? -15. Divide both sides by -5. What does x equal? 3. X equals 3. So we're trying to figure out, by the way, the problem says to find the length of QT. So if we're finding the length of QT, we first have to solve for x. It's 3. Now we have to substitute in the value of 3 back into the original 4 times x plus 8. Now that we know what x is, it's 3. So 4 times 3 is 12, and 12 plus 8 is 20. The other thing we could and probably should do, just real quick to verify that this is correct, is if you plug in 3 for x over here, we should also get 20. 9 times 3 is 27. 27 minus 7 is 20. So both of those segments end up equaling 20 when we plug in for x. So that means we did it right. It's all good to go. So something down here I want to talk about before we turn the page, down here at the bottom. In terms of what there is and isn't in terms of information, enough information, if we take a look here, it says, in the figure below, there's not enough information to conclude that BD bisects ABC. And the reason for that is, even though the distance between A and D is the same as the distance between D and C, we don't know if from D to A is the distance from this point to that line, because the distance from the point to the line has to be perpendicular, and we don't know that it's perpendicular here or here. So even though we know the segment lengths are the same, we don't know that those are actual distances between the points and the lines. So there's not enough information there. We would have to have proof that we have right angles at A and at C in order to make that work. All right, go ahead and turn the page. Try this one on your own. Right here. Find the length of SP, just like we did on the first example. You need to set up an equation and solve it. You can do that in the margin notes over. You can do that in the margin notes over here if you want to. Do you know Leonardo today? So, what equation do we need to write in order to solve for x first? Yep. Nice. 3x plus 5 is equal to 6x minus 7. We know that those two segments, MS and PS, have to be congruent because we have an angle bisector. We know it's an angle bisector because of the congruent markings here and here. And we have perpendicular between M and S and between S and P, which means that the distances have to be congruent because the angle bisector is perpendicular to those two sides. So let's go ahead and solve this. I'll just go ahead and subtract 6x from both sides. So that'll give me negative 3x plus 5 over here equals negative 7 over here. If you subtracted 3x from both sides, that's totally fine. It's not going to change your answer. Then I'll go ahead and subtract 5 from both sides on this as well. Negative 7 minus 5 is negative 12. So if we divide by negative 3, what does x equal? 4. All right, x equals 4. We're trying to figure out the length of SP. So if we plug in 4 for x right here, 6 times 4 is 24. What's 24 minus 7? 17. All right. And just to make sure it checks out, 3 times 4 is 12. 12 plus 5 is 17. So it works for the other one as well. And it's a really easy thing to do to check the other one just to make sure that they both end up equaling the same distance. Because if they don't, that means that signals to you need to go back and figure out how to change something else to actually make it work. All right. Questions there? Cool. Kind of going back to what I mentioned before is like a lot of the math is just very, very similar between different types of problems. Same type of math we did yesterday on these types of problems with a different theorem though. Example 2. Let's move right along. Using the converse of the angle bisector theorem. So this one says, we've got perpendicular distances between x and w and between w and z, and they are congruent because they're both 5. Because they're both 5 and they're perpendicular on their distances, that also means that w is on the perpendicular bisector of this angle, which means that that part of the angle is congruent to that part of the angle. And by the way, that 38 is talking about that part right there. I know it's kind of like really far away from where that angle actually is, but that's what it's describing, is that amount of degree there. So because wx is perpendicular to yx, so wx perpendicular to yx up here, and wz, this one here, is perpendicular to yz, that one there, and wx is congruent to wz, those right there. W is equidistant from the sides of angle xyz, and because of that, yw is the bisector of angle xyz, cuts it in half. So something is congruent to angle xyw. What angle is congruent to xyw? Yeah, zyw. Nice. Which means that the measure of angle zyw is equal to the measure of angle xyw. Look at that. That's the definition of congruent. We used that a bunch when we did proofs. Anytime you go from congruent to equals or equals to congruent, that's the definition of congruent. And look at this. We got a column here. We got a column here. It's kind of like writing a proof. And then we're going to substitute. How many degrees does angle zyw equal? 38. It's the same as the other one. They're both 38. Now, that was a long way of doing this problem. The short way is just to use what's already there and just write the answer. So what's the answer for this one? 37, yeah. Measure of angle JKL is 37 degrees. What if this said, I'm going to add a question here for you because that one was way too easy. Those segments JL and ML are congruent. They're also perpendicular, which means that KL cuts angle JKM in half, which means that this part of the angle is congruent to that part. We just figured out measure of angle JKL because it's the same as the one underneath it. What is the measure of angle JKM? How many degrees is angle JKM? 74, yeah. Got another question for you. What is the measure of angle JLK? Not quite. It is 53. How come? Yeah. Why'd you do 90 minus 37? Yeah. Okay. How many degrees are in a triangle? 180. Okay. So if triangle JLK up top here is a right triangle, that means that 90 degrees of those three angles is taken out by one angle, which means between the other two, JKL and JLK, between those two angles, they have to add up to 90 because one of the angles was already 90. So if you take 90 and you subtract the 37-degree angle, that's going to give you angle JLK, which is right here, which is 53 degrees. Nice. Which would mean that angle MLK is also 53 degrees. That one right over there on the other side. Cool. The only reason I ask those questions is because you will have to use that kind of math as you're working through the assignment today. So I figured it'd be good just to do a quick review on that. So, actually, I want to check something out on the online side here real quick, because it gives us something to look at before we move on to the next type of problem. So I do want to take a look at that real quick. Huh. Let's see how that works. Ooh. Yeah, go for it. Actually, we'll go ahead and skip that for today. Let's move on to the next page. Not quite what I was expecting that to be. So let's have a look here at yeah. Yeah, to be in the hallway, you have to have one. There's time and dates. Okay. So angle bisectors of triangles. So we talked about angle bisectors of angles. Now we're going to be talking about angle bisectors of triangles. So basically yesterday and the day before, we talked about perpendicular bisectors of the sides of a triangle. Now we're going to be talking about angle bisectors of the angles of a triangle. So because a triangle has three angles, it also has three angle bisectors. That makes sense. Each of the angles that in a triangle could be cut in half. The angle bisectors of a triangle are concurrent, kind of like the perpendicular bisectors. Concurrent just means, what does concurrent mean? Anybody remember? What's that? It's in your notes. Flip back a few pages. Go to page 350. What does concurrent mean? One more time? Not necessarily equal. Yeah, concurrent means that they all intersect at the same place. Yeah. So the three angle bisectors of a triangle will all intersect at the same place, which in general is called a point of concurrency. But specifically with perpendicular bisectors, it was called the circumcenter. With angle bisectors, that point of concurrency is called the incenter. So here we go. Another theorem. The incenter theorem says the angle bisectors of a triangle intersect at a point called the incenter, and that point is equidistant from the sides of the triangle, which is exactly what we just saw with angle bisectors a moment ago, but now we're talking about three angle bisectors within a triangle. So basically, if you focus on, let's try to cover this up a little bit. If you focus on just this angle here, angle A being cut in half by AP, that means that the distance from P to D is the same as from P to E. So those two segments are congruent. If we just look over here at angle C, CP is the angle bisector, which means that PE is the same distance as PF. So we can put another congruent marking there. And then if we did the same thing for B, that would be true as well. PD is the same as PF. And so if you focus in on just the angle bisectors, it's the same as what we saw back over here, but now we're looking at an entire triangle instead. So if P is the incenter, it's the point where all three angle bisectors intersect, then PD, PE, and PF are all the same distance. And we're also broken down into right triangles, just like we were with the perpendicular bisectors, but these are not perpendicular bisectors. If we were to draw a perpendicular bisector here at BC, for example, don't write this down, but if we did, the perpendicular bisector would probably be right around here, not here. So the incenter and the circumcenter are definitely different locations on most triangles. Not on all triangles, but on most triangles. Okay. So if we head down here, these problems are going to be really similar to the ones that we used yesterday and the day before. So P is the incenter of triangle XYZ. Find the measure of angle. So now we're talking about angles. We're trying to find the measure of angle LZP. First of all, it'd be a good idea to identify where that is. So I'm just going to underline that in red. And if we check out LZP, that's that angle down there. We have to figure out how many degrees that angle is. So it's going to walk us through this first problem, and then I'll have you work on one on your own, and then we'll move on to the final page. There's only two more problems after this page. So P is the incenter, which means that XP bisects angle LXK. XP is here. It's bisecting angle LXK. And ZP right here is bisecting angle LZJ. And YP is bisecting angle KYJ. So what that means is that the measure of angle LXK is twice the measure of angle PXK. PXK is 24.6. So the one next to it right here is also 24.6. So that means everything at angle X adds up to 49.2 degrees. So the angle at X, both of those angles at X add together to equal 49.2 because they're each 24.6. Likewise, down here, the measure of angle KYJ, everything at angle Y, is the combination of both of the 25.1 degree angles. So if you add 25.1 with itself, you get 50.2. So the entire angle up here at X is 49.2. The entire angle down here at Y is 25.1. So we're going to write those in right here. So we're going to say 49.2 plus 50.2 plus the measure of angle LZJ, everything at angle Z, which we don't know yet, adds up to equal 180 because the three angles of a triangle have to add up to equal 180. So if you add those two numbers together and you subtract them from 180, what's left? How many degrees is angle LZJ? What'd you get? I think 89.6. Oh, okay. Take away 9. Yeah, you take away 9. 80.6, yeah. 80.6 degrees is the measure of angle LZJ. That's everything at angle Z. We only want half of that because we're trying to figure out angle LZP, which is half of LZJ. So right here, because ZP bisects angle LZJ, that means that twice the measure of LZP is equal to LZJ. We already know that LZJ is 80.6, so that means that LZP is half of LZJ. So that means that LZP is half of 80.6. Again, this is the long way of doing this. There's a much shorter way of doing it that we'll look at in a second. Or what's half of 80.6? 40.3 degrees. Nice. So the answer is 40.3 degrees. All right. Again, that's the very long-winded way of working through it. All those things are true, but there's a faster way of making that happen. So mostly it's going to be faster because we can use symbols a lot of the time, and we can use markings on the diagram to represent the words that were said here, which I would much prefer. So let's look at this next problem here. So J is the in-center, which means that all of these three segments right here are the same length, which isn't really going to come into play in this problem, but it is true, so we may as well put it on the diagram. In addition to that, JB is the angle bisector of DBE, which means that that side is 33.9 and so is that side. JC is the angle bisector of angle DCF, which means that this angle here is congruent to that one there. JA cuts in half angle EAF. So those are congruent to each other down there. We're going to figure out two things here. We're going to figure out the length of JF and the measure of angle JAC. So two separate types of things that we're going to be working on. We have to figure out a length in a right triangle. So if you're figuring out a length in a right triangle, what do we usually use for that? How do you find the length in a right triangle usually? What's that? Sure, if we knew the length, yes, we could certainly do that. But how do you find the individual length? So we're trying to find JF, right? And if you look at lengths in triangles that we have right now, we have two lengths in triangles right now. We've got 9.4 and 10.6. We have to use the Pythagorean theorem. We could use HL to say that like this length over here is 9.4. That would be fine. But even after you use HL, you'd still need to use the Pythagorean theorem to find out what's missing. Yeah. Yes, we have 2 out of 3 sides in a right triangle. One of them is a leg, 9.4. 10.6 is the hypotenuse. So we're going to go ahead and I'm just going to do the math over to the right side here in the margin. So we got more room. So let's write this out. 9.4 squared plus, what do you want to call this length between E and J? X, sure. All right. So plus X squared equals the hypotenuse squared. So that'd be 10.6 squared. So this is what we did yesterday and the day before. We're still doing that with right triangles. So 9.4 squared is 88.36 plus X squared equals, let's see, 10.6 squared is 112.36. So let's go ahead and subtract the 88.36 away from the 112.36. That's interesting that they have the same decimal. Oh. It's kind of convenient. So X squared equals 24. And the square root of 24 is almost 5, right? Round it to the nearest 10th. What do you get? What's the square root of 24? Yeah, about 4.9. So X is approximately 4.9, which we just solved for EJ, but JF is the same. So actually putting those congruent markings there did help us. So if that one's 4.9, JF is also about 4.9. So we can just write 4.9 after JF. So Pythagorean theorem to find a missing length of a right triangle. Now we're switching gears and we're talking about degrees for this next one. Measure of angle JAC. Which one's JAC? What angle is that? Angle JAC. The triangle itself is large, but the angle JAC is actually the same angle as angle JAF. That's the same angle. It's a different triangle, but it's the same angle. It's that right there. Whether you're talking about JAC or JAF in terms of an angle, not a triangle, but an angle.
Oh, wait, sorry.
Yeah. Just the specific angle itself, JAC and JAF are the same angle. They're not the same triangle, but the same angle. Yeah. So we're talking specifically, yeah. So how do we find the measure of that angle? I mean, don't give me an answer yet, but tell me how you figured it out.
I figured that one.
Yes. Yes. Subtract it in from 180, yeah, and then good. Exactly. It's exactly what we did in the last problem, because if you're trying to figure out this angle here, then it's going to be good to know the entire angle here, which would then be good to know the entire angle up here and the entire angle over here, which we can do. We can get those ones, because if you double that, you get everything in C. If you double this, you get everything in B. And we're just talking about the entire big triangle that goes around everything right now. So if you double 33.9 and you double 28.5, you get these two numbers here. So 28.5 doubled is 57, 33.9 doubled is 67.8. So everything at angle B is 67.8 degrees. Everything at angle C is 57 degrees. If you add those together, you get 124.8. So those two angles, those large angles together equal 124.8. So if you take 180 and you subtract 124.8, you get 55.2, which is everything down here at angle A. We need half of that. So 27.6. So measure of angle JAC, 27.6 degrees. Are there any questions about that? I know I didn't show really much work for that, but if you remember how many degrees are inside of a triangle, that's kind of the big thing here, because if you can piece together a triangle and figure out another angle that's within that triangle, or part of an angle within that triangle, or specifically half of an angle within that triangle, there's a lot of ways to go about doing this. Now, that's not the only way to solve this problem. There's a lot of other ways we could have figured out this angle right here. We could have said, because here's another way of solving this one. You ready? If this is 28.5, that's 28.5. This is a right triangle right here. And this right triangle is going to be congruent to this right triangle here. Well, actually, you know what? It's not. Those are going to be congruent. Those will be congruent as well. So, actually, I don't know if we should do it that way. Never mind. Just kidding. There is another way to do it, but it would actually be, it'd be more work than we need to do. Let's forget that. Let's not think about that. Let's just do it this way. Okay, turn the page. Any questions before we move on? Let's keep it as simple as we can. How about that? All right. We got a couple of problems that we need to work out in terms of actual like designs. So looks like a school building. Hey, it is a school building. Okay. A new art sculpture is going to be placed in the courtyard of a high school. The courtyard here is outlined by the blue triangle with vertices A, B, and C. So the entrance of the courtyard is located at points. The entrances to the courtyard are located at points A, B, and C. Find the location of the center of the sculpture so that it is equidistant from the sides of the courtyard. So this one's going to be a little bit tougher for us to do because angle bisectors are going to be a little bit harder to come by. Angle bisectors are not something that are going to be super easy to have us just like draw in. So I will go ahead and show you how to do this, but I'm not going to have you answer a question specifically like this one on your assignment today. So actually though, no, that actually doesn't work. Never mind. Okay, so everybody come up and grab compass and a straight edge again. We're gonna do this as just sort of an example, but if there's a problem like this in your assignment, you're not gonna have to do it. So come grab a compass, come grab a straight edge. We're gonna do some angle bisector constructions on this little guy here, and then after that, we'll answer the one at the bottom, which will be a lot easier. Just the Ducks game here. Okay, just all right. If anybody cares about March Madness, the Ducks are playing there. Oh. Yes. All right. So we talked about how to construct perpendicular bisectors the other day. Today we're going to be constructing angle bisectors, and with an angle bisector, what we can do is it's actually pretty similar to what we had before. So if you go ahead and just take your compass, open it up to put your point on A, and just open it up to some length, not too long, and put yourself, give yourself a dot on the blue line down below. Just put a dot using that opening, keep the same opening, and then put a dot on the blue line on AB. So you have a blue line, dot on the blue line AC and a dot on the blue line AB. Mine are here and here. And it doesn't really matter how far they are. It's kind of up to you on that first one. Then, yeah. So just open it up to a certain amount and then put the point on A and put a dot on the blue line AC and then put a dot on the blue line AB using that same width of opening. Yeah, as long as it's the same width, you're good to go. All right, now, try to remember this one correctly. Measure out the distance in between the 2 points. So basically put the point of your compass on one of the blue dots and put the pencil on the other blue dot. So match up that width in between those blue dots using your compass. Okay, then out in the middle of the angle, so in the green area here, just put an arc with your point on the bottom blue dot or the top blue dot, either way, and draw an arc through it out in the middle of the angle, and then switch it. Put the point on the other blue dot and then draw an arc through as well. And you should be able to intersect both of your arcs. And that point right there, is going to be on the angle bisector of that angle. So then you're going to take your straight edge and line up this point of intersection with the arcs with point A. And draw your line. And that should be cutting in half angle A. Or roughly cutting in half angle A. It might not be perfect. Mine's definitely not. In fact, I could probably do a better job of that. There, that's a little better. All right, now we're just going to do that with one more angle, because while all 3 angle bisectors intersect at the same point, 2 of them also intersect where all 3 of them will. So we only ever need to do 2 of these. So let's use B as the other one. So with B, I'm just going to open up a certain distance. I'm going to put a marking on the blue line BC, and then I'm going to head over to AB and put a marking with the same distance away. And again, it doesn't really matter how wide you open it, but open it to a certain width, put your point on B, put a mark on the blue line BC, put a mark on the blue line AB. Then measure the width between those points. So point on one, pencil on the other, and then go out somewhere out here and draw an arc with the point on one of those dots on the blue line. I'm starting with mine on AB. I'm going to flip it around over to BC. the point on BC, and then get my arc through there as well. And then this point is on the angle bisector of angle ABC. So this point lines up with point B. Which one are we talking about? Down here? So did you get your point on line BC? Well, you have a blue dot on the blue line on BC. So just open it up to a certain width, put your point on B, and then just put a mark on the line BC. Keep the same width and then go over to line AB and put a point as well on that line. Yeah, so do one on BC and AB, but the same width for, when you rotate it around. Once you do that, open up your compass to put the point of your compass over on the dot on the line AB, and then put the pencil point on the point on line BC. So you're basically just measuring the opening between those 2 points. Now that you have that, you're just going to go out here and then keep your point on that blue line there, and then just mark it way out in the middle of the angle. Like do an arc way out in the middle of the angle, which is going to be below it basically. And then flip it around and then put your point on the BC point and then draw another arc through it. And you should get the 2 arcs to cross each other. The 2 arcs should cross each other, yeah. And wherever they cross, line up that point with B and then draw a line with your straight edge between that point and point B. So once you have that, wherever those 2 lines intersect, right here, that is the end center. So that's where the sculpture should go. And if you look here, it says the intersection of the angle bisectors appears to be at about 8.3, 4.4. If you take a look, you go over 8.3-ish, and then you go up 1, 2, 3, 4.4, 4.5, right around there. Yeah, that looks good. So that ends up working. Now, if it asks you to do something like this, again, it's going to be hard to do this without an actual compass. So if there's a question like this on your assignment, I'm not going to have you do that. But if we take a look, I'm going to draw some blue lines here. This point right here, if we draw a line perpendicular to this blue line here, like that, it should be the same distance as if we draw a line perpendicular here, which should be the same distance as if we draw a perpendicular line here. So those 3 segments should all be roughly the same length. That's the idea with this. That's our end center. So that segment congruent to that one, congruent to that one. All right, one more problem. There we go. Let's see, what are we out of here today? 12, no, 149. Wow, cool. We're gonna have a lot of work time today. Oh wait, no, we're not. Sorry, I completely realized we're only, never mind. We're only 10 minutes out of class. I read that wrong. Okay, one more problem. We'll have about 10 minutes of work time. Okay. So here we go. Tyrese's parents want to install a hot tub on the back deck of their house. The back deck is outlined in that blue triangle. The vertices of the deck are located at X, Y, and Z. Find the location of the center of the hot tub so it's equidistant from the edges of the deck. If necessary, round your answer to the nearest whole number. So what we're going to do on this one is, well, it's going to be a little bit different. So first question here, how many degrees is this angle here at Y? 90. Okay. So a 90-degree angle is going to be a lot easier to cut in half on a grid, because all you need to do is go diagonally down through the grid lines. So perfectly diagonally through the grid lines that way. So if you go ahead and just put, I'm going to put some dots on here, make them show up a little bit better. So you get a point there, My pen from the other side's bleeding through a little bit, so it makes it a little bit harder to see where to put these points, but I think we'll get it. There we go. It's about like that. We don't actually need to use our compasses for this one. So there's a problem like this where it's like, you know, nice and diagonal like that. It's not going to be too bad. So there's our angle bisector there. Now, how many degrees is it angle X? Was it 45? Yeah. Angle X is a 45-degree angle because that's 90. The deck then has a 45-degree angle. So what would half of 45 be? 22 and a half. Yeah, exactly. So you could use a protractor if you had one, which we'll give it a try. So the protractor, you go with a 22.5-degree angle on your protractor, which can measure out the angles that you want to measure out. So you just put that in the middle. If you ever used a protractor, they're actually, I think, a little bit simpler than using a compass, because if you go to 22.5 here, that looks like it's completely backwards. So hang on just a second. All right. We'll set that there. A 22.5-degree angle. Well, actually, it needs to be 22.5 if we're going this way. There we go. That'll be better. Okay. So 22.5 puts us at about roughly about here. And so this is more of an estimate than anything else, but that's about 22.5 degrees. Now, if you want to estimate these, you certainly can. You could use the compass if you want to, or if you had your own compass, you can use your own compass. But that actually looks relatively accurate because we've got ourselves a nice point right there where those two things intersect. So we take a look. So this is 1 right here. So if we go 2, 3, 4, and then up 1, 2, 3, 4, 5, 6, 7, 0.47. That's where those two are going to intersect. So 47. Again, if there's any questions where you actually have to like make constructions with like protractors or compasses or things like that, I'm just going to go ahead and delete those from your assignment. So that's all I got for you for notes for today. We got through everything we needed to, which is great.